the big picture, right?
Maybe you can just say next, because I did say
okay. No, it's good. I didn't exercise today, so it's good. Well, it's actually two pictures. So one picture worth 1,000 words, two pictures, 2,000 words worth of information up there, which is the background for all our nuclear, the nuclear shadow, kind of Jungian thing. So on August 6, 1945, and on August 9th, 1945, the United States dropped 2 nuclear weapons on Japan. When you look from way up, you saw the mushroom cloud due to the way, well, I could go through the physics of it. It's not so interesting right now. What's more interesting, or more tragic, I should say, is that several 100,000 people were killed there. And so I think when people think of nuclear energy, they think dangerous, but really deep down in the unconscious, it's bad, right? Because we can do this. So we shouldn't do bad things. But that's like saying we shouldn't use electricity because you can electrocute people, which was Thomas Edison's argument for not using electricity. That is, Thomas Edison, the light bulb guy, he was in a feud with another scientist, Nikola Tesla, who was favoring, so Tesla was favoring alternating current, which is what we all used, and Edison wanted his baby direct current. So in order to prove that Tesla's alternating current was really bad, what did he do? He got Topsy the elephant. Now, I've never gone and seen Topsy the elephant. There are, videos of Topsy the elephant being electrocuted by alternating current, and that was Edison's, point. What's the result? We use alternating current, and we also developed the electric chair, so we got the best in both worlds. What I'm trying to drive at is that just because we can use nuclear energy for bad things doesn't mean we should give up nuclear energy for the good thing. Okay, so I'll come back to that at the end. Two slides, nuclear energy. A reminder of what we're all made of. Yes, we are all made of that stuff, although it's not red and blue and green, and it actually doesn't look like a little solar system. So that's an atom. A nice cartoon that'll be good enough for us today. You've got neutrons inside, don't have any electric charge, protons here in blue, and electrons in green, and making this whole thing electrically neutral. And here, if you count the number of protons, it tells you what chemical element that is, and this is carbon. And that makes up plastics and trees and us, to some extent. And this is really small. Really, really small. So this is 1/10 of a billionth of a meter across, right? A meter being about a yard. And so if you imagine trying to pack, the whole population of the Earth, 6 billion people, into 1 yard, imagine how small everybody has to be to fit in there. Really, really small. That's the size of an atom. And this picture is not to scale. Not only is it fake, we know from quantum mechanics that atoms don't look like this, but it's completely wrong scale, because the nucleus, that is the protons and neutrons right here in the center, they are about 1/10,000th of the size of the whole atom. So a speck of dust in a football field. That's most of us, most of the world, most of the universe is empty space. But that's for another talk. That can get really depressing. So now, happy stuff, fission, right? Let's make energy, okay? So we're going to make energy, and how are we going to do it? We're going to take a neutron, one of those uncharged particles, and send it flying into another nucleus. And if we do it just right, we choose the nucleus right, say we choose uranium or plutonium, and we have the speed of the neutron just right, what's going to happen is the nucleus is going to get hit, smash into 2 daughter nuclei, if you have this family, kind of feeling, or fission product if you want to be more general, and other neutrons. And one more thing comes out, which is not depicted here because it's hard to draw it, is energy. You get heat out of it. And one equation, this talk I promise only one equation, but it's the equation, right? It's the one we all know and love. Thank you, Einstein. So how do you get this energy? Because you lose mass. If you add the mass, so you weigh all the stuff that comes off, and you compare it with the weight of the stuff you started with, you've got less at the end. And some of that matter was turned into energy. And because c, the speed of light, is so big, very little amount of matter gets you huge amount of energy. And that's why nuclear power is so attractive, because you can get so much of it from so little. Okay, but now that's just one reaction. How do you make this into something useful so you get a little bit of heat? Big deal. Well, you can repeat it. Because maybe, well, if you notice, let me just go back a second. So you have 1 neutron, right? Out came 3, 1, 2, 3, right? Huey, Dewey, and Louie. Sometimes you actually get two, as I'll show in a moment. So now you can take one of these neutrons and do it again, and again, and again. You see if you have more neutrons than you started with, you can see how this thing can multiply, and you can get lots and lots of energy. So here's shown a little more in detail, your uranium-235. So what does that mean, uranium-235? That means the total number of protons and neutrons in the nucleus is there's 235 of them. And one neutron comes in, it splits into two nuclei. I guess energy here is yellow, right? Heat, that's the color. The sun, right? So, okay. And it's split into two nuclei, and three other neutrons came off, and it's now something, they can do something. So one case, they hit uranium-238 in this particular example. And the reason, they show in this diagram uranium-238 is because most uranium is uranium-238. It's the naturally most abundant form. And so when you have your uranium in your reactor, in your weapon, you don't want to have this around, because this guy just swallows up the neutron and end. No more reaction. So you're trying actually to get a lot of what's called enriched uranium. Have uranium-235. If you're going to make a bomb, you want it really enriched. But so you have your some uranium-235. That can react with a neutron, split again, and two more neutrons, more uranium-235. And you can see if you have enough uranium-235 around, whoop, out it goes. Lots of energy, lots of neutrons, more reaction, more reaction. Guess what? It's called a chain reaction because you have a chain of reactions. Yeah? Okay, sometimes, by the way, shown here is a neutron can just go off and not react with anything, and then you've lost it. So this is the basic physics of that goes on in a nuclear chain reaction. Where does it differ from a bomb to a reactor? So in a bomb, you just want to have it as fast as possible. Of course, you want to have it as fast when it's in the enemy's land, not when you have it. So you do a little precaution. You make sure that they're separate, two pieces of, say, uranium or plutonium, and then you deliver it. Surprise, express delivery. Boom, they come together. The chain reaction goes. Hiroshima and Nagasaki. But if you control it, if you're a little nicer, and you absorb some of the neutrons, that is, you make sure you only get about one, a little more than one, then you can have this not skyrocketing off and without making lots of energy without any control, but you can determine how much energy comes off, at what rate. And so that's what you do in a nuclear power plant. And so maybe you've heard of control rods. It's all in the news right now. That's what's controlling, how much how fast this reaction is proceeding by absorbing neutrons. Okay, so that's the basic physics. Now what happens in a plant? Not the green thing. Yeah. Okay, so you have a plant. What do you have? You have your nuclear fuel in here, your uranium, colored in red, I guess, dangerous. And then you have control rods. That's the material that's going to absorb the neutrons to make sure it's a controlled reaction and not a bomb. How do you get energy out of it? Because you've got now heat, but you've got to do something with it. And so what you do, one simple design, is you heat up water. There's water all around. You heat it up. It forms steam. The steam goes out to a turbine. What's a turbine? A turbine is just a big machine to take steam and turn it into something spinning. That's all. All the engineers in the room will get upset when I say that, but that's all it does. You have some steam going through and something spins. Now why would you, that seems like crazy. You can have a top, right? Why would you do that? Well, if you have a turbine spinning, you can get a generator spinning. And a generator spinning gives you electricity. Out comes the electricity, you power your house, you're happy. But you have to complete the loop, because now you've got steam in here. What are you going to do with it? Well, if you cool the steam, you've got water again, and you can keep this going. The water is now cold, it gets heated up by the nuclear reaction, and you just keep going through and through and through. So an important component of all of this is a condenser, something that cools the water. This water is not water, it's still steam here. You want to cool it, something that takes away the heat, cools it, sends it back. Now why did I choose this particular design? Because this is actually from the the Nuclear Regulatory Commission. You thought it was just like a little sketch. This is the little sketch that the American government is showing to everyone of how nuclear power plants work. And it's actually animated, because when you go to the website, you see the little drops going down. And that makes you feel real safe, right? I chose this design because this is the design that's in Japan. This is exactly how it works. One more point, of course, is that you want to protect yourself from radiation, right? You've got steam, you've got a nuclear reaction going on, so you bury it in a lot of concrete. This containment structure, and so the radiation, there's multiple layers here. They show one, so that hopefully, well, as we found in Japan, it didn't work out quite well, but in principle, it protects you from what's going on inside. Okay, so oops, let's go back. Am I actually doing anything, or is it no? Okay, I can just stop. What does that? Finally, 6 slides later, you realize it. This is what the power plant part of the power plant looked like before the accident. You see the first 4 reactors are there. I think this one is here, and then 4, and they produce a lot of power. They produce, I didn't realize how much power. So in Japan, 25% of its electricity comes from nuclear power, and this plant at full capacity produces 1/10 of that. So 2.5% of all of Japan's electrical power is coming from 6 buildings. 2 are further there, are up in the right-hand corner. Only 3 of them were in operation when the earthquake struck and then the tsunami came, but that is only partial consolation, as I'll explain in a moment. So 3 of them, 1, 2, and 3 were actually, the nuclear reaction was going on, 3 were off. What happens when the earthquake hits? Well, they're not stupid. They decided that the reaction will stop. So when the ground accelerates too much, immediately the control rods drop in, absorbing the neutrons, the nuclear reaction stops. So there's no nuclear reaction going on right now in Japan. That stopped a long time ago. But you have a lot of heat. And that's a problem because this, I told you, produces a lot of energy, and now you have to get rid of it, but it's hard. I'll explain what happened in the next slide. So 4, 5, and 6, I just want to say they were down. There was no nuclear reaction, nothing had to be stopped. But again, in 4, there was still heat being produced from when it had been turned off earlier for maintenance. And so that's why the reactors actually that you maybe hear in the news are 1, 2, 3, and 4 are the principal damaged one. Okay, so this is the picture after. As of, I think this is March 16th, yeah. So very different picture, right? 4 reactors, 1, 2, 3, 4, explosions in all 4 happened. And so what exactly happened? Can we go back a couple of slides? Let's just test. Yeah, there, perfect. What happened was the cooling system failed. So, because you have a tsunami, an earthquake, a tsunami. So earthquake, reaction stops. Tsunami knocks out power to all of northern Japan. Now they had a backup system, 8 hours of diesel generators to keep it going, but in 8 hours after a tsunami of that magnitude, there's no electricity still in Japan. So this fails completely, no more cooling. All your water is going to get converted into steam, the pressure is going to build up, boom, explosions. Actually, one of the reactors is a little more complicated than that. There was hydrogen which was generated, and that reacted with the air, and that exploded. I think that was in reactor 4. So can we go back to, yeah. So all explosion, and some of the explosions released radioactive material. Yeah, they're in the air, and they're here actually. They're in the U.S. They've come to visit, but it's not that bad. I mean, it's hard to say. We're looking good. Actually, if you look right now. This is a great site, by the way. If you want to know what's going on right now, the New York Times is updating all the time the status of the reactors, and they're doing a good job of it. And in fact, right now, the pressure is constant at the reactors, temperatures are either stable or dropping, so it's optimistic. I mean, still, there are workers, everybody fighting, trying to cool these guys. So the problem is, what's going on right now is you want to cool this like crazy. So the simple schemes, you have no power, although now it's back in a couple of the reactors. Your pumps aren't working, so even if you have the power, it's not sure the pumps will work. So what do they try to do? Well, try to put it out like a forest fire. Go in and come with a helicopter, boom, but if you look at the videos, it just vaporizes. This is at, thousands of degrees, so it's going, all this water. They also try to pump seawater. They're still doing that. Again, it's not perfect, but they're fighting it. The next one? Great. So, but what's the danger? Okay, so you have the big boom, and now if you're there, that hurt, but nobody actually has been killed, if I'm correct, from this nuclear power accident, which is amazing. What's the real danger here? The danger is the radiation, the radioactive isotope. So there's actually, it's in 2 parts. One is, briefly mentioned, the spent fuel. There's fuel that's was used previously, it's being stored nearby, and it could release radioactive elements as well. But the thing that got airborne are radioactive, isotopes that are formed in the nuclear reaction. So remember the daughter nuclei that split up? Well, they can come in different forms, and a couple of them, well, more than a couple, but the two main ones that are nasty are iodine and cesium. You may have heard of them in the news. The iodine is bad because it can get into your thyroid, and you need it. So you need iodine in your thyroid, and then if you are exposed to huge levels of it, you get thyroid cancer. The good news about the iodine is that in 8 days, it's sort of, well, half of it goes, what's a half-life? Half of it goes away, decays away in 8 days. So in a matter of weeks, all the iodine that was released will be harmless. That's not true of the cesium. Cesium-137, that's going to be around for a while. For those of you who remember Chernobyl, I was living in Italy at the time in Chernobyl, 86, I think. Yeah, the cesium in the alienation zone, I think it's 30 kilometers around, about 20 miles around Chernobyl. Nobody can go and live there. Nobody can do anything except scientists and the people who have to maintain the reactors, because it takes 30 years for the cesium to decay to half of what you had at the beginning, and then so it's going to be for hundreds of years. But before we panic about cesium, there's cesium in this country from all the Cold War testing we've been doing, all the bombs we left, that we detonated in the 50s and after that. Yeah, there's cesium around. The question is how much of it is there. Right? So just hearing that there's some radioactive isotope out there is not enough to panic. You need to know that there's really a lot, and fortunately there isn't really a lot. So where's the danger? If you're right next to it, yeah, there's some danger. If you're a worker cleaning up the plant, yeah, you may have some health problems. That's what happened at Chernobyl, and people died at Chernobyl. But if you're outside, and that's right at the plant, if you're within 50 miles, there's a slightly elevated risk they're talking about, but nothing that would cause any immediate damage or harm. They found radiation from the plant has reached the West Coast. How do we know that? Because we've been really good over the past 50 years at detecting radioactive isotope, because we were really worried that the Russians are going to let a bomb go. So we wanted to know, every time somebody was testing, we could detect minute amounts of the, say, cesium. So we're really good at detecting small amounts, and we found them on the West Coast, but there's 100,000 times less than what you normally get from, like, the ground. So we're not in any danger at all, completely not. And even, if you're 20 miles away, it's not so bad. There is, of course, concern of this getting into the food supply, and they've already showed in Japan it's slightly elevated because, it gets into plants, cows eat the plants, it gets into the milk, but we're talking 7 times the maximum amount, 2 times, not numbers that are any cause for concern. I remember in high school going out in the land checking the radiation levels with a Geiger counter. Yes, I was a physics geek. Actually, the physics teacher didn't want to teach us that day, so he said, why don't we give you all Geiger counters and you go out and see if you're going to die soon? Right? And the answer was no, because it was twice backward. Yeah, because we were in Italy and the explosion had happened in Chernobyl. Okay, so we are not in danger, which doesn't mean we shouldn't, think about what's going on. Great. And that's the part that it gets me really, I would say, pensive about all this. Because the reaction to this crisis, in some cases, has been so irrational. So the favorite one is taking the potassium iodide tablets, right? You may have heard of this. So what are you supposed to do when the radioactive iodine comes out, which is taken into your body as iodide? That's the ion. There's an important difference there. So you're supposed to take potassium iodide. Why? Because if your body has all the iodide it needs, it won't take any more from the environment, and in fact, it'll just pass it through you and it won't hurt. And that's okay. Except what's been happening? People have been going crazy, you see, and buying potassium iodide like mad. If I really put my physics knowledge to use, I would have bought the whole stock or futures of potassium iodide, and made a killing off this, but I only realized later on. And what is interesting in Japan, there have been no cases reported in the hospitals of radiation sickness, absolutely none. But then I think a dozen cases of potassium iodide overdose. Because, it's again, so that's one twist. The other one is the iodine iodide craze, right? So the purple stuff that you put on to disinfect the wound, that's iodine. That's iodine in the element form, not the ion form, which is the iodine. And that is useless in protecting you, and will just burn your esophagus when you do it. And people, I guess, like, that's what radiation feels like, right? Crazy thing. And it goes to preposterous things that when people tell them not to do this is from British Columbia, they're getting calls like, "What are you covering up?" And like, well, no, there was no disaster. There's no cover up. But it's just propensity to think of fear and everything bad is going to happen. And it's not. But that doesn't mean you don't get to think about it, and that's the other attitude I want to encourage, which is of respect. Yeah, please. This was sobering. I hadn't really thought about this until I read it. This is Michael Golay is a professor at MIT of nuclear engineering, and he said, I think it was in 2003, where a Japanese power company approached him and other people to say, look, what happens if there's a big earthquake? There already was a big earthquake in '78 where they were trying to see what would happen to the reactors. It was not as big as this one. It caused about 1/3 of the acceleration that this one did, and nothing happened. But they said, what's going to happen if there's a really big earthquake? Tell us. And the conclusion they came to was, yeah, if a big earthquake comes, the nuclear power, the reactors are going to be in a problem, and there could be a radiation release, and it could be bad. But if there's such a big earthquake, so many more people are going to die from the earthquake itself and the tsunami. We should put our resources into tsunami drills and into making better buildings and not the nuclear power plant. In fact, Japan did a really good job with tsunami evacuations. There are some villages that have been practicing for 40 years on a daily basis, warning to, and I mean, you have to have a discipline, because I know if I heard a warning every day for 40 years, eventually I would ignore it. I mean, like, not again, but they didn't. And that's why so many people could escape. Now, we don't know what's the total number of people going to be affected by this nuclear accident, but we could use Chernobyl, which is a worse accident, as a limiting case. Let's just take some numbers. They're sobering. So, in Chernobyl, a few hundred people died right away, mainly the workers at the plant. And then there were a few thousand people who developed cancer that probably they wouldn't have developed from being exposed to all the radioactivity. Okay, so those are the numbers we're talking about. Immediately a few hundred deaths, then a few thousand deaths. And Japan is going to be nowhere near that. How many people have been killed by the tsunami itself? 7,000, 8,000, and there's still 10,000 missing. I mean, I don't want to compare, lives, but when you have a finite amount of resources as a country, you have to make a policy decision. Where are you going to put the resources? And the Japanese made the right decision overall. That doesn't mean we shouldn't make better reactors, and probably the next generation is going to be designed to survive even these big earthquakes, much bigger one, and it's going to, and maybe, I don't know, build them underground so it's easier to, pour concrete on them. The Chernobyl option, which people are talking right now, which is, maybe in Japan you'll have to do what they did in Chernobyl, just bury the whole thing in concrete and tell people not to live there. But it doesn't look that bad right now. So I think that this approach is actually a healthier approach. That doesn't mean you don't disregard the dangers, but you weigh it, everything together. Which so brings me to the end, which is nuclear realism. You have to weigh the pros versus the cons. So let's do the pros is really mainly one thing. The same amount of nuclear sort of uranium can give us much more power than the same amount of coal or oil. Much, much more. So the light bulb example I showed behind, you can light one light bulb for 180 years, and with coal and oil the same amount will light it for 4 or 5 days. By the way, for those, I should mention, 1 kilogram is about 2.2 pounds. So that's huge. Now, we know there's danger. We know there's a radioactive waste. That's a problem, and we have to deal with it, and any other release of radioactive isotope. But no greenhouse gases. No greenhouse gases. And people also forget that burning coal releases radioactive elements that were trapped really nice inside the coal. You burn it, they get out into the atmosphere. So if you're going to make a judgment, you have to look at all the factors, and which includes, cost. It includes, do you want to depend on foreign countries for your source of energy, or do you want to be self-sufficient? So, to end, I will finish with the phrase that I was taught by Professor Michael Rubiner, who taught me when I was a graduate student at MIT. He did a chemical safety training course, and 3 words he said just stayed with me now that I have my own lab, which is respect, not fear. When you're dealing with something that's potentially dangerous, that's potentially harmful, you have to respect the dangers, you have to think about them. But fear is not the appropriate response. It will not lead you to a healthy place nor to the right decision. And with that, I'll be happy to end and take some questions. Thank you.